Okay, so let's start the presentation. Maybe some people might join, but let's start off. I only have 45 minutes, and I can talk for hours about this technology. So this is the agenda for today. I'm going to talk a little bit briefly about flash usage in a virtual data center, the PernixData FVP architecture, then I'll go into detail about the fault-tolerant write acceleration, and then I finish with restructuring data flows. So we all know that storage is one of the last unsolved problems in our data center. And virtualization is requiring low performance, is requiring high performance storage, a lot of capacity, and especially scale out. And that scale out performance is something that traditional arrays are not very good at. You just buy a box and you have a limited amount of devices, the space for the devices itself. So most storage vendors, they come up with the idea of let's add flash to the mix, and yeah, let's wait. Not a good idea. Well, let's start off again. I think the room is more filled up now. It shows that you always have to listen to women. Thanks, Jay, for pointing it out. So, to recap, virtualized data centers require scale-out performance. And scale-out performance don't really work with traditional arrays because of the limited space and the limited amount of IOPS of a traditional spindle. So one thing that most vendors thought of was let's add flash to the mix. Now, where do you add flash? There are two dominant locations. It's either in the array or it's in the server. Now, each of those locations have their own challenges. If you're going to place flash in an array, you're going to put a low latency device behind a relatively high latency network, and it's shared as well. So usually that destroys the whole benefit of having a flash device. Another thing is, the other location is putting it into the server. Now, if you put a flash device in the server and you're just installing a data store on it, you're losing out the mobility features of a vSphere cluster everybody loves, right? DRS, vMotion, and even HA. So that doesn't work. So we came up with a different solution. And that different solution is not about changing location, but it's putting flash in the server and clustering it. Creating a cluster so that you can still use your vSphere cluster features, such as DRS and HA and vMotion and maintenance mode. Now, because of that, and because you can move around your virtual machine and can use the flash performance, you create a different tier. You create a storage performance tier in your data center, and you allow the array to do what it does best, and that is providing raw capacity plus data services. So your array becomes your storage capacity layer, and you will get your storage performance from the Pernix data layer, from the compute layer plus flash plus Pernix data. So let's take a closer look at the FVP architecture. Now, in the FVP architecture, there are two main elements. The first element is the Pernix management server, the Pernix MS. Now, that is primarily used to feed the UI in the vSphere client. So it creates, it allows you to create flash clusters, and it allows you to actually look at the performance data and look at the usage of your FVP cluster. The Pernix MS server is not a part of the data path, so it's not a critical component. The critical component in this is the extension model. It's the kernel module that we install on every host. And by installing it on every host, we are actually extending the storage stack inside the ESX host. You need to add a flash device to your server to your ESX host, and that can be either an SSD or a PCIe. We don't care, as long as it's on the HCL of VMware. You can even add multiple and mix them in a single host, because we virtualize the flash device. And when you install the extension model, it allows you to create an FVP cluster. And by doing that, you will virtualize all the flash devices in the Pernix host. And that flash cluster will create one seamless pool of flash resources used by the virtual machines in your vSphere cluster. And when you run a virtual machine, or when you add a virtual machine to the FVP cluster, we call it you accelerate a virtual machine. And then you can use and create a write policy that can either accelerate reads or accelerate writes as well. Now, when they show me FVP for the first time, this was actually one of the two things that blew my mind. This was so amazing that I still am in love with this part, and that is the cache coherency. Because what FVP does, it actually knows all the versions of data of a particular virtual machine inside the FVP cluster. Now, why do you care? You care because you have vSphere cluster features like DRS or vMotion, right? So what happens if when a virtual machine runs, it creates a flash footprint on its local server, and that flash footprint accelerates the data, that accelerates the I/O operations. But what if DRS moves the virtual machine from host A to host B? What happens then is the virtual machine is getting treated by a cold flash device. So there's no acceleration. Because FVP knows exactly where that data resides, it will select that data and it will pick it and it will transfer it to the local host again. So it will see that if the virtual machine moves from host A to host B and the virtual machine does the write operation. FVP knows that, hey, I got that one and I got it on host A. Let me get it for you. So the moment it grabs it, it brings it up, it bubbles it up to the virtual machine, and it copies it to the local flash device. So the next time the virtual machine reads it again, it will have that same data on the local flash drive again. So during the life cycle of the virtual machine, we try to keep the flash footprint as local as possible. We use the vMotion network for this. So we support 1 and 10 gig networks for this. Now, like I said in the beginning, when you accelerate a virtual machine, you select a write policy that can be write through and write back. You can accelerate on a virtual machine level or on a data store level. And when you accelerate on a data store level, you will actually creating a default policy for that data store, so that all the recent virtual machines that are running on that data store, they will get that write policy. But also, the newly provisioned virtual machines will automatically get that policy attached to the virtual machine. Now, when you accelerate a specific virtual machine, and for example, this virtual machine, the orange one, is configured in write back, that will override the data store write policy. So you can use a more granular approach as well. This is very helpful for environments that are based on SLA performances or similar type of virtual machines, such as a VDI environment or a storage DRS cluster that is using the same type of storage. Right? We even have a customer who uses this in a vCloud director where they have provided VDCs based on SLAs, so that tier 0 has got a connection with the data store cluster, and that data store cluster contains accelerated data stores by FVP. So the moment their customer is deploying a virtual machine in that provided VDC, the vCloud director asks the storage DRS cluster to provision the virtual machine on a data store in the data store cluster, and FVP will automatically attach the default write policy to it. And you don't have to do anything again. Now let's talk about write through and write back. Let's revisit that. So write through is primarily accelerating read operations. And why is that? Because when a virtual machine issues a write operation and it hits the kernel, FVP will hijack that I/O and it will fork it, it will split it, and it will write to the flash device and will send it down to the array. Now it only acknowledges the write back to the virtual machine when it receives the acknowledgement from the flash device and the array itself. So the effective latency is all the way down towards the storage system. So for writes you don't get the acceleration primarily, but for reads you do, because the next time the virtual machine reads the data, we're going to service it from flash. Now I said you're not primarily accelerating writes, but because you accelerate a lot of reads, you're going to reduce the number of IOs hitting your array. So eventually you're going to save bandwidth, you're going to save capacity, compute capacity on your array to handle the writes. Write back is the holy grail because it accelerates both reads and writes. When a write operation is sent by the virtual machine, the FVP code hijacks it, writes it to the flash device, and immediately acknowledges it back to the virtual machine. So there's a really low latency when you do this. Now there's a second loop, and that second loop is not in the same, is not run at the same time as the primary loop of acknowledging it back. It has done this on a different time scale. So what it does, when the I/O hits the flash device, we're going to write it to the array, and that is transparent to the application. So it doesn't matter anymore if the storage system is completely overloaded, because we will take care of that write toward the storage system. Now, because there are two different loops, there is a time factor to consider. And with the time factor, there's risk involved. Because the moment we acknowledge the write back to the application is going to think it can read that data again. So if that host fails at that point in time and that virtual machine is being restarted by HA on a different host, and it will read that data, the storage array will say, I don't have that data anymore. So because of that, we need to create some fault tolerance. And we do that by creating redundant write data. We do that by creating replicas of data. So the moment you select write back as your write policy, you will get an additional question. And that is, how many replicas do you want of this data, of this particular virtual machine? That can be either 0, 1, or 2 replicas. So if you select 1 or 2 replicas, and in this case I selected 2, the ESX host will write every bit of write data towards 2 different flash devices in the FVP cluster. Now, normally the source host will issue the write to the storage array. But what if the host fails? If that host fails, FVP knows it, and it will instruct one of the replica hosts to destate the last bit of write data towards the storage system. So the data is always safe. Now, think about the overhead of write data. We only send the write data to the replica host, so we don't keep a complete flash footprint on multiple hosts. So that means that there's only a small fraction of the overall flash footprint available on the replica host. And I made a screenshot, and I don't know if you can read it from the back. But on the local host, that virtual machine has got a little bit more than 200 megs of flash footprint on the flash device itself. But it only has 512K of data on the replica host. So if the host fails, if ESX02 fails, the host that is actually running the virtual machine, ESX03 is going to destage, that's the act of writing the data towards the storage array, is going to destage 512 bytes of kilobytes of data towards the array. And when the virtual machine is getting restarted by HA, it will have all the data on the data store again. So let's go over the fault-tolerant write acceleration. Now, one thing you need to know is that although acceleration is our goal, data integrity is our key. We must make sure that your data is safe. And everything in the code will show you that. So a question I usually get is, what happens when I have a virtual machine and write back, and the virtual machine issues an I.O. In the moment it issues an I.O., the host dies. Well, in that case, there's nothing wrong because the virtual machine didn't get the acknowledgement back. So it's treated like every other failure in a normal system as well. So what happens when a virtual machine writes an I.O. or issues a write I.O., we're going to accept it, and we're going to write it in parallel to the local flash device and to the remote flash device. If both flash devices acknowledges that write, it is then sent up towards the VM. So from that point on, only then the application will know that the data is safe. So if the ESX host, the local ESX host fails, we are always certain that the data resides on a remote flash device. And in that case, the remote flash device will send it towards the array to keep it safe there.
What about power loss?
Sorry?
Power loss?
It's exactly the same. If we don't acknowledge the I.O. back to the application will treat it as a normal data loss and will send it back and send it again. Or when the data loss occurs on the host, the other host will have it, and it will detect that the source host is down, and it will start to destage the replica data.
Yeah, but it's the 2 or 3 hosts that all have the data in flash, and then the acknowledgement is sent to the VM.
Yeah.
And then just before the data is sent to the storage system, all the hosts die of great power.
Every host down. Yeah. Okay. So then you put, so your virtual machine is down as well?
Yeah.
Okay. So when the power comes back, we still have the data because it's a flash device, it's not memory. So it's a non-volatile resource. Now, even, this is cool because even if your host just basically burns down, but your flash device, let's say a miracle happens and your flash device is still good, you can actually pull it out, go to another host that hasn't been burned down, put it in, and FVP will see that there's still on destaged data, and it will send it down to the array as well. And the key is it's a flash device, right? But we'll come to certain disaster scenarios later on. That's a good question. So what happens if there is a failure in the system, right? The last thing you want to do is keeping track of every component to make sure that the data is safe. So we do that for you. And we do that for you by automatically transferring write policies back to write through. And when you do write through, all the data is always safe because it's sent to the local flash device and to the storage system before we acknowledge. So if a flash device fails, local or remote, one of the replicas, or if the vMotion network fails, or if the replica host fails, FVP does 2 things. It does an automatic transition from write back to write through, and it will select a new replica host if something happens with the replica host. So let's take a look at a flash device failure. Let's say the replica host has a flash device failure. FVP detects it. We're going into write through mode for the virtual machines who are in write back. on that host that is using that other replica host. And then it will run in right through until the error is solved. Until you switch when you install a new flash device, we will detect it as well. And then we seamlessly transition back to write back again to give you the best performance. But the key is always have the data saved. So we always go to write through when there's a problem. Now, every host has 2 replica hosts assigned to it. That is done by the Pernix MS server. Now, what if a replica host fails? The virtual machine on the local host is still good. It still runs. It still can use the flash device. So it can be accelerated. But because we cannot guarantee the policy, because we cannot guarantee the data availability, we're going to switch back to write through again. And we're going to let Pernix MS solve this by selecting a different replica host that is still functionally perfectly, that is capable of sending the data to the data store. Right? So if it finds a different host, it will select that host. And after the selection is complete, we will transition the VMs to write back again. And then we can have the acceleration to its fullest degree. So these things will show that we are looking at data as the most precious thing in the world. We don't want to accelerate just to accelerate. The first thing is data integrity. Now, one of the coolest things is, because we have this D-stage area, that's the area where the writes are being kept until they're being written to the array, we can actually start restructuring data flows. And if you look at your current environment, is that readable? The black in the back, Jay, can you read it? System 100K, okay. I thought it was more light, so I blacked it down. So at the top, you have a compute cluster, 4 hosts, and it's connected to a storage system that delivers 100K of IOs. Now, when you add more virtual machines, at one point you need to add more ESX hosts. That does sound familiar in your environment, right? Yeah. So what happens is you're going to do a performance scale out on compute resources, but your array remains the same. So your array still provides 100K of IOPS, but now need to basically distribute those amount of IOPS to the new systems as well. So your performance spy, each part per host is getting smaller and smaller because it's getting diluted, right? If you have a equal distribution, if DRS does its thing, right? Now, this is the most current problem. What happens if you install FVP on it? You create an additional performance layer. And in the top, I installed, on those 4 hosts, I installed 4 fusion cards. Each host has a fusion IO card. And I'm taking here conservative numbers. Let's say each fusion IO card can deliver 50,000 IOPS. And I've seen environments which reach up to 80 or 90 IOPS per fusion IO card. Now, at this point in time, the FVP cluster is providing 200 IOPS. 200 IOPS to the virtual machines you decide to accelerate. This becomes your deterministic performance layer. You decide. How many people use storage IO control? How many people try to use storage IO control and then discover that it didn't work because there was an external workload running on your storage array? Nobody? Yes, there's one. I've seen many. I've actually troubleshooted so many environments where they wanted to use storage IO control but couldn't because there were external workloads on the array itself, eating up the IOPS, eating up the performance of the array itself. You don't have that problem with this anymore because there's no external workload running in your FVP cluster. You are the only one providing the performance to your virtual machines, right? Now, if you need more hosts because you're running more virtual machines, you're going to scale out not only compute, but also performance independently of your array itself. So this is the first time you can actually scale out storage performance apart from your storage array. So your storage array still delivers 100K, and your FVP cluster now delivers 400K. And think about the cache coherency, what I was talking about. Because FVP knows exactly where each version of the blocks are, you're going to use the other flash devices as well in your cluster. So it's not a per host basis. It's an overall pool of flash resources. Now, because we use the vMotion network, we're using an Ethernet network. And an Ethernet network is a point-to-point connection. And point-to-point connection have one of the tremendous abilities of not interfering with communication that happens between other hosts. So if replica data is sent from host A to B, it doesn't interfere with a remote flash access that happens on host C and D. You use the crossbar network that is in an Ethernet network to get the best performance. This is much quicker than going all the way down to your storage array. Typical arrays have latency figures of 5 to 10 milliseconds. We've seen performance, we measured performance on 10 gig networks in the range of 400 microseconds when we did a remote flash access. 400 against 10,000. That's the difference we're talking about. And if the flash device can handle it, you're good to go, right? And the beauty of it is, because we are flash agnostic, you can add flash towards your server if there's room, right? Because we keep it in that layer, we're reducing the number of IOs going down on the storage array network, down on the storage switches towards the shared storage controllers, to the shared storage ports, to the shared disk spindles. We refrain from that. And in the UI, we have something we call hero numbers. And this is cool to show to your manager, because this is a screenshot I asked the customer to take for me this week. And they are running data analysis. And this is the amount of bandwidth saved when they start using FVP. Now I have another customer who's using iSCSI networks, and they had a talk with their storage vendor, and the storage vendor said, well, we might switch over to fiber channel because your iSCSI network is completely bogged down. Because they used FVP, it went down to 65% again, instead of the flatline 100% they were used to. Because they just saved a lot of IOs going down to the storage system. Right? Now, all of this and all of the destaging area provides an additional benefit. I talked about the two different loops, the loops that don't run simultaneously. And because we can actually we save the data on different hosts, because we know the data is safe, we can actually start to time manage the IOs going down to the array. Like I said, data integrity is one of our key goals or our rules. That means that we don't change the number of writes going down to the array. That means that we need to change the flow of the IOs. Because if you have an application that is spiky and it creates and it bursts IOs, if you do that same thing going down to your array, so if you mimic that burst from the flash device to the array, you're not solving performance problems because you're just delaying the bottleneck. So what we do with that D-stage area, and because we know the data is safe, we can actually create a more uniform write performance structure. The flow of IOs are getting stretched out because we are able to time release it. Now what will happen if a virtual machine issues a write? We're going to try to destage it as fast as possible. But we know about fairness, and we know that other virtual machines are hitting the array as well. So we're going to stretch it out a little. Now I captured one of the performance graphs of an application. It's the same one, but I blew this one up. So what will happen? The green line is the I/O sending IOs to the or writing basically to the host. So you see here 8800 writes are being issued by the virtual machine, and it's being serviced by the flash device itself. Now the application is happy because it will get the IOs and it will get the immediate acknowledgement, so the latency is very low. Now that doesn't mean we're going to spike and we're going to send the 8800 IOs back to the array immediately, because that doesn't solve the problem. And that's where the blue line comes in. And that's the line that is actually being sent out to the data store. So what you see here is that on that particular time, 1800 IOs are being sent towards the array. That's a more decent number that the array can handle, right? That is the performance that is actually provided or need to be provided by the array. Now I said before with the cache coherency, that was one of the things that blew my mind. This is actually the other one. Because what happens here is now you can actually start thinking about how your array should look like. Because you don't have to design your array to actually take care of the spikes, what we used to do before. We used to calculate the number of spindles because at one point in time application will create so many IOs, blah, 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 blah. Because we time release, the number of IOs are getting reduced just over a longer period of time. And because the data is safe, there's no need to worry about it. This will impact your array configuration. Because now you can think about capacity. Now you can think about, if I just create my array and give a decent performance, I only need to look at capacity again. Now the I/O per gigabyte pressure just completely went away. You can think about, and they released a statement last week that, or a couple of weeks ago, that they had 6 gigabyte disks based with helium. Now, that footprint of those disks, the amount of disk you need for actually the capacity will diminish your footprint on your data center. You don't need to have that large array anymore. You can just look at capacity and data services and let FVP take care of your performance. So what are the next steps? Get some flash, download the file, and start accelerating your virtual machines. If you don't like it, you can just remove the virtual machines. Because we install in the kernel, you don't have to install anything on the virtual machine. There's no agent you need to install. There's no driver you need to install. You don't need to change the configuration of the virtual machine. You don't have to specify the amount of flash you want to reserve for that virtual machine. We just take care of that. There's no extra data store you need to manage, or a virtual appliance you need to resource manage that takes care of the storage. We are a kernel module, right? You don't need to change anything of your data store or your storage area network. So what happens is that your old virtual machine is running on the same old data store, on the same old array, but magically faster. And that's basically it. Now we have some cool new Kingston drives. We got them from to test, and they were actually pretty good. I really like the Intel ones, the Intel 3700 line. In some of the cases, in almost every case, it was on par with the Intel ones. In some cases, in some of our tests, it was actually even performing better. So it's really impressive drives. And we got some to test, and I actually asked them, can we give some away? So if you sign up, we basically give some away to people who sign up, right? So this is my presentation, and I opened up some, left some time left for some questions. So,
what ESX version do you need?
we run 5.1 and 5.0. We are working on supporting 5.5, but it's not out there yet.
What kind of CPU overhead should we expect in the hosts?
It depends on the workload you're running, and it depends on how many virtual machines you are running, and it depends on how many replicas you are running. So it depends on your workload, how many things you are throwing at the FVP. But it's a kernel module. So what happens is that we're not hogging one CPU. The kernel is allowed to run on every CPU there is, and we just follow the kernel. The kernel extension model is not a service by itself. It's just adding code here and there. It's all based on public APIs and on a public framework of ESX, the ESX kernel itself. So there's not a service that is hogging up all the CPU. So we just enrich the code.
Do you have any practical experience in terms of the lifetime of the flash drives running on very data-intensive data centers?
Yeah, we have, and one of the things we did, we try to avoid write amplification, and we try to avoid things that will burn through the program array cycles of a flash device. So we took care of that by not using a file system, and we not using a RAID system and all that thing that increases write amplification. But if you look at the current flash devices, Intel is quoting 5 years if you refresh your complete data footprint on the flash device itself. So if you erase the complete device every day, then you still have 5 years to work with that flash device itself. You're not going to erase your full flash device every day. So.
No, but it still has a lifetime far beyond the meantime between cleanup for the
Yeah, but that is completely dependent on what you do with it, and then also how the over-provisioning structure of the flash device itself works. That's totally different on each flash device.
Is it possible to control where the replicas go and results in a stretch cluster?
Yeah, great question. So we are working on that. So now you can actually do it via the command line. You can do anything you want with PowerShell. So every command you can do in the UI, you can do it with PowerShell. You can actually do even more with PowerShell than in the UI at the moment. But you need to do scripts to actually get that working. And one of the things we don't like is to use scripts for solely configuring stuff. So if you look at the pedigree of the company, almost every engineer is coming from VMware. The engineers that are working on the UI are actually not coming from VMware, but they are coming from Google. They are ex-Google people. And they want to do it as clean as possible. So what we're working on in one of the future releases is actually creating some way of marking certain clusters as groups where you can point and say, okay, I want to use this group to store my replica. So you can do two things with it. You can actually say, I want to have my replica on another data center, like Struts, or you can do the counteractive way and say, no, I don't want to traverse that line, so I want to keep my replication inside my host or inside my own group. But that's something that's future music, right? So we're working on it. In the back?
Yeah.
There's one thing I remember from the beta, which caused me a bit of headache, which you may have improved from the production of. I remember that if there was a previous file location table on the device you want to use from Pernix, it refused to touch it. Is there any way of easily overriding an existing DNS if you really want to?
Good question. I think we just now, when you have something on your flash device, we don't notice it, or we just override it completely. That's it. Because when you add a flash device to an FVP cluster, because we don't have a file system on it, because we don't do a RAID system, we want to own and manage that complete flash device, similar as vSAN. What's the question?
To divide the flash between reads and writes. I mean, certain workloads generate a lot of writes that will never be read again.
Yeah. So we thought about that, and one of the options you can do is write around. That's one of the things that you classify the data as being, well, useless, because you're never going to read it again. But that's very, very difficult to use in a system that is using a cache coherency status across multiple hosts, because at that point you need to think about which data to keep and which data to invalidate. So we don't do anything active at the moment. We are investigating it. For most of the part, we rely on our heat maps. So what happens when I/O is being written to the flash device? It's hot because it just appeared on the flash device. But if it's not accessed, it's getting colder and colder and colder. And at one point, we allow, if there's no, let's say if there's no pressure, we will keep it on the flash device because there's no harm done. But if other applications want to use the flash device as well and has hot data, we will basically evict the coldest data out there. So we don't worry about that. So that's the thing we're doing right now. But we are investigating other ways as well to with more intelligence. In the back?
Yeah, on the subject of flushing the cache, do you reorder the plots to be sequential when possible?
No. Yeah.
How much cache is enough?
Thanks, Paul. Why don't you answer that question yourself? No, it depends on the amount of workloads you're generating. And one of the things we say is, take a look at the UI and look at the eviction rate. We keep track of how much data is being deleted from a flash device while it's hot. So that's an indicator where you want to add more flash resources to your flash cluster.
Would that just be additional drives?
That can be additional drives, yeah. So another thing is, look at the working sets of your application. And one of the tools you can use is from Cloud Physics. They will have a tool which shows the working set of an application. It's not 100% accurate, but it will give you a guidance on the working set. And that's the active part of the application that is used to actually perform. And then you can start to think about the sizing of your flash devices. When you talk to one of our SEs, he can help you as well with determining the flash size of your flash device. I think I'm out of time, so one more question.
Yeah, think of how old is the company, how many are devoted to research and development, and what is your, are you represented in the Nordics or?
Yes, okay. So we were founded, I think 19 or 20 months ago. Our founders are ex-VMware. Satyan Pagani is the ex-storage CTO of VMware. He invented VMFS, link clones, what else? A couple of other things. All our other storage engineers are also ex-VMware. So this is one of the things I I'm very proud of. Because we are ex-VMware and because we invented most of the storage stack within VMware, we don't have to guess when we think about some cool new technology that runs in the vSphere kernel. Because we wrote the code itself, we actually know how to improve it, right? The other founder is Pujan Kumar, ex-VMware, ex-Oracle. He invented Exadata, the in-memory database system from Oracle.